And I'm presenting frustrated magnetism in ternary rare earth sulfides. So what are frustrated magnets? Frustrated magnets are materials in which localized magnetic moments or spins interact through computing exchange interaction that cannot be simultaneously satisfied, giving rise to a larger degeneracy of the system ground state. So the ternary rare earth sulfides I'm working on adopt either a disordered cubic structure with space group FM3 bar M, or a layered alpha sodium oxide type rhombohedral structure with space group R3 bar M. What's the motivation behind this research? So frustrated magnetic materials containing rare earth ions have potential application in quantum information science, like magnetic resonance imaging, MRI, global positioning system, GPS. They can also be, charcoal coordinates can also be used as scintillators, which are materials that convert high energy gamma rays into photons. Excited by this application, we began the synthesis. So polycrystalline samples of ternary rare earth sulfides were obtained via high temperature solid state method. Stoichiometric amount of sodium sulfide, rare earth, and sulfur were ground in glove box and placed in a graphite crucible. The crucible was sealed in a caustic under vacuum and gradually heated to 850 degrees Celsius, kept at that temperature for 48 hours, and slowly cooled to room temperature to obtain the rhombohedral. The cubic phase was obtained by rapid cooling to room temperature. So this is powder X-ray diffraction pattern of cubic sodium praseodymium sulfide and rhombohedral sodium praseodymium sulfide. So the ternary rare earth sulfides prepared in our laboratory adopt either a cubic or rhombohedral structure. So to the best of our knowledge, we are reporting rhombohedral structure of sodium praseodymium sulfide for the first time. Our powder X-ray diffraction pattern, which is the open cycle, match with the calculated pattern, that's the red line. So the refined unit cell parameters obtained using Red-Weld requirement are in good agreement with previously reported work. So this is a plot of temperature dependence of magnetic susceptibility within a temperature range of 2 to 300 Kelvin and applied magnetic field of 1000 Oersted. So the magnetic interaction was investigated by performing Curie West fitting from 150 Kelvin to 300 Kelvin. So the negative Curie West temperature here, which is minus 80 for the cubic and minus 93 for the rhombohedral phase, suggests antiferromagnetic coupling in the two structural types. So there is good linear relationship at high temperature in both the cubic and rhombohedral, and no obvious magnetic transition is observed in both structure type. So optical band gap of sodium rare earth sulfide obtained using torque plots constructed from Kubel-Common transformation of the diffuse reflectance spectroscopy data shows that all the materials are semiconductors. So this is direct band gap of sodium cerium sulfide, and this is indirect band gap of sodium cerium sulfide, suggesting that both are possible. So we hypothesize that the band gap can be tuned in two ways. The presence of F electrons may affect the optical property. So this is 4F0 in lanthanum with no F electron density to F1 here in cerium with 4F1 with F electron density. So you can see how the band gap is decreasing from 3.15 without F electron density to 1.91 electron volt. Or if there is structural distortion, the band gap will change. So here is rhombohedral sodium praseodymium sulfide, and there is structural distortion in this 3.03 electron volt direct band gap, and then it reduces to 2.75 electron volt in the cubic phase that is without a structural distortion. So in summary, the rare earth ion is antiferromagnetically coupled in sodium praseodymium sulfide, and no obvious magnetic transition is observed, and all the compounds show semiconducting behavior that's within 1 electron volt to 3 electron.